Hello and welcome to another episode of Fun Times in Statistics. So today we're going to be doing describing data using numerical measures. So there's going to be a lot more calculating today. You might want to get your calculator ready. We're going on a ride. I would say that because it is more calculationally focused today, you should think about how you would use, some of these applications to what you might do in the future for your job prospects or your major. And once again, there are going to be a couple things that are covered in your textbook that we are not necessarily going to do. So let's get into our objectives. Sorry, I call these objectives. They're outcomes. I tend to get those two words confused because they're very similar. So we're going to talk about the different, what we call measures of center, which are the mean, median, mode, and then on top of that, we're also going to discuss the weighted mean. If you've never heard the word weighted mean before, it's just a different type of mean where you want to weight stuff. And well, I'll get into that more later, but basically there's one you already know about and are fairly familiar about as a student. Your GPA is actually an example of a weighted mean. Fun facts. We're also going to do box and whisker graphs, which are kind of fun. It's one of my favorite graphs. I think it's a very quick way to tell what your data looks like. We're going to do the measures of spread, which are the range, variance, and standard deviation. Oops, I missed interquartile range. Two of these are more useful than others. We're going to spend a lot of time with interquartile range and the standard deviation, and not so much with the other two, but they're still good to know. I like the range simply because it's one that's fairly quick, which is also nice. And then we're going to finish up by talking about z-scores. So you notice we're not doing outcome number 5. I'm saving the empirical rule for when we talk about the normal distribution, because that's where it belongs. If you've heard the word empirical rule before, you know what I'm talking about, so we're good. We don't do Chebyshev's theorem in this class. If you want to take a look at it, it is kind of a cute little estimating tool, but it's not the most useful in the world. And we're also not doing coefficient of variation for the same reason. Again, they're a nice little estimating tool, but not very practical once you have actual samples that you're dealing with. So let's get into it. Let's start off with looking at some centers. So when we say center, I want you to be thinking like middle or typical data. It's location where I feel like we could describe the data's center. You know, what's in the middle. It would be like if your boss came up to you and said, hey, how much do our customers typically spend on products? What do they usually do? It's the one that comes up the most often, so to speak, is one of these. And they're just different ways of trying to describe what typical is. And for some data sets that one of these makes more sense than the others. For some of them, you can do a bunch of them together, and they each kind of tell you a little bit. And I did include weighted mean in here as well because it is technically a center, but it's very different from the other three. Usually the traditional measures of center are mean, median, and mode. Although mode I consider more of a shape. We'll get into that. All right, so we've mentioned parameters in statistics before, but just to make sure that we know what they are and remind ourselves of what they are from all the way back in chapter 1, a parameter is something we compute from a population, so it's going to be a number that we gather from a population, whereas a statistic is going to be something we compute from a sample. So if I did my mean from a population, that would be a parameter. If I did my mean from a sample, that would be a statistic. That's the difference between the two. So it's kind of fun. In the class, you get to say what the class is. Statistics. There are many statistics. All right. What are we going to look out for? So again, I already said center is going to be like just one value. I also think spread is incredibly important. One of the reasons why you want to spend time talking about spreads as well is just that the center only describes one thing, what's typical. It doesn't tell you at all about what the possible values could be. So what I would say is pretend you just produced a new fun scented candle that you're planning on putting out into production, and you're trying to convince your different stores to sell your fun candle. I don't know why I picked a candle. It's because that's what I can see in a painting in front of me. Just live with it for now. You've got this product. You know what you need to charge to be able to make a profit, so you'll include that in your estimate. But what stores should typically charge would be just the average. Whereas you could also look at what is a range of values I would consider acceptable for my pricing. Maybe I'm okay with it being somewhere between $2 and $20, and on average I want it to be 10. So there you go. The center there would be 10, and my spread would be from 2 to 20. And you can see where spread is kind of helping you understand what are the possibilities. So I particularly look at center and spread when it comes to battery life on my laptop because, well, I would like it to last a long time. And I also want to know when it's doing something wonky. If you've ever run it in eco mode, you know that it lasts a little bit longer. So there you'll get like a range, maybe it's from 7 to 12 hours, but you know typically it lasts you about 10. Knowing the range tells you if that it only lasts 2 hours fully charged, something has gone wrong, right? You know what the spread possibly could be, not just one value, the center. Alrighty, that was a little too much. Now you've seen these images before. Remember, data can have the same shape, same spread, but different center, and see how these are all just slightly different, with the light blue graph at the bottom being slightly, well, much more different than the other two. You can also have the same center but different spread. So knowing just one isn't enough. If you know just the center or just the spread, you don't have enough to really tell what your data looks like. So here they all have the same center but very different spread. So actually the smallest spread is the yellow graph in the middle. The next up, or the medium in the middle kind of spread guy, would be the light blue, or I guess I'll call that a medium blue graph at the top. And then the one with the most spread is actually the sort of cyan blue one at the bottom, because it has its data more spread out. So you might be confused into thinking the yellow one isn't as spread as the one above it. Sorry, the middle one as the top one. But because so much of the data is at the center, there isn't a whole lot of variation from the center. So that's what we're going to be looking for in spread here, is not just like a range where it goes from 300 to 500 like both the top graph and the center graph do, but also how much of my data is spread out that far. So if I had something where I had, like just a couple values at 400 and then a bunch at 100 and a bunch at 800, that would be much more spread than if I just had a bunch at 400 and one or two at 100 and one or two at 800, because more of my data is far away in one of those scenarios. So spread's going to do some interesting things. Alrighty, so here's some descriptions for this, for the measures of center. The mean is something you've probably seen before. It's the arithmetic average is its technical definition. That is the one where you add up all your data and divide by how many there are present. So we like to think of this as the balancing point by weight, where size really matters. So if I have $1 versus $10, it really, really is important. Whereas the median doesn't care about size, it cares about order. It wants to be the midpoint of the data. So it wants to be so that half the data lies above and half lies below, and it doesn't care so much about how big each of those values are or how small they are. So you can imagine the median isn't going to be affected by size changes or anything different happening there. And then the mode is just the one most frequently occurring. And the mode, honestly, is going to be one you don't use as much when it comes to doing trying to describe the center of your data, but the mode is incredibly important. It's one people easily forget about. I personally tend to use the mode and find the mode getting used more when it comes to ordering of objects, knowing which sizes or which shapes are the most frequently occurring or most frequently used can really help with that process. So there you go. Here is how you calculate the population mean. So in looking at this, capital N is just the number of items in your population. So if you've got 100 people in your population, the N would be 100. And what this is saying, this S big, so this is called capital sigma, that big E looking guy, that's actually supposed to be an S. Isn't that fun? Go math. As you look at this, the sigma notation just means sum. Add them all up. So add up all of my values, my population, my xi's, and divide by the number that you see. And then this funky looking U isn't supposed to be a U, it's supposed to be a fancy M to stand for mean. And it's just the average of all the values in your population. So fancy looking M, also known as mu. I've heard it pronounced both mu and moo, so you're either a cat or you're a cow. Feel free to enjoy that. Either way, we're talking about the population. Meow. All right. Here's a quick little example of that. So if we look at a local hospital and their number of patients in the hospital every day changes quite a bit, as you can imagine. So here's their census of what's happening in the last 10 days. So this is considered a population because I'm doing the entire hospital over a 10-day period. Okay, and so you're going to add all 10 of these up, which is what I'm doing right down here in that fraction in the middle of the bottom of the page, and divide by 10 because that's how many days we did this. That's how many are in my sample. And you'll see that when you add that up and then divide, you get 288.4. I kind of rounded a lot there, but hopefully that's understandable to you. Hope that makes sense. You ready? So physically, one way you can think about the mean, and this is fairly common, is we think about it as if the graph had weight, it would be the balancing point. So if you imagine that x-axis we're looking at here as being like a board, and then I took the blue bricks and stacked them on the board, representing it into a histogram from what we did in chapter 2, where I would place a wedge so that this would balance like a teeter-totter would be at the mean. And you can actually do this if you've got like a ruler spare or handy and a pencil. You can use the pencil as a mean and then take the ruler and then place different items that are hopefully the same size on different places on your ruler, and then find the mean by finding the balance point on the ruler. So if you have some dice laying around that are all about the same size, for some reason my house is always full of dice. I blame it on the fact that I used to teach a class with 30 people and we did lots of experiments with dice, so I bought 100 count bag of dice. I don't know, the cats play with them, it's fun, but you can balance them. There's some apps online that allow you to do this too. It's kind of fun. I don't know what kind of spare time you guys got. Why am I wasting time talking about this? Anyway, here's another example of the population mean. I've got 3 variables to look at here: rooms rented, revenue, and number of complaints. This is from the San Carlo Hotel data. I stole this from your textbook over an 8-week period. So my N here is going to be 8 weeks. Another way you can always think about N is also the number of items recorded. So since it was recorded for 8 weeks, there you go. So I could actually do 3 different means here. So if I want to do rooms rented, I could just do the average of these two. I've also got a note in here about what the Excel function is for this in case you're an Excel user. We're obviously going to see how to do this using Minitab as well, so look forward to that. Although Minitab tends to be very sample focused, just as a warning, that's why I have this in here. And it's very important that you know that, because Minitab is based on using real data to do real calculations. In all honesty, you very rarely have a population to work with. You more often than not have a sample. And watch out for that, because there are some Excel functions that are very specific to using population versus sample, especially the standard deviation, which is one we're going to see in a little bit. Hello, I've recorded this for 3 times now. Oh boy. So what we're going to look at now is how can I measure spread around my data and why that might have some problems. So ancient mathematicians a long time ago in a galaxy far away were really working on how can I describe how things are spread around the mean. So if a mean is a good balancing point, how do things deviate from the mean, or how far away are they? So if you remember back to algebra, when you first learned about subtraction, you always learned it as distance away. So really this is looking at how much is x, my variable or my values, away from the mean. Remember, mu means means, so x minus the mean. So here I've got the number of rooms rented, each of those values, if you remember that from the previous slide, or you have the notes open and you can look at that. And all I've done from this first column is just subtracted the mean in the second column. And so if you look at all of those, some of them are negative, some of them are positive. So when the value lies above the mean, it comes out positive. When it's below the mean, it comes out negative. And when you add all those up, you get 0, because the mean is in the very dead center by size. So of course, if I look at all their distances around it, it should be that when you add those all up or look at all of them, it's balanced amongst all of them, and therefore there is no deviation if you add them. And this was a problem, and we're going to see how it gets fixed later. It's kind of interesting. All right, let's talk about the sample mean. So it's the same idea, except for your sample size is n. So you're just add them all up and divide them by a little n. So notice we like to use lowercase when it comes to sample stuff because it's a smaller grouping. It's one way I remember it myself. And then the other thing is that when it comes to doing samples, we almost always mark them with headgear. So we put something on top of the item. So in this case, we use a bar. So if you can see a bar on anything in the future, you'll know that that means that it's an average and it's about a sample. So I mean, you could do average age, and it would just be age with a bar on top of it for a statistic about age. I like to make a joke that I was always meant to do statistics because my last name is Barr. Terrible jokes. Good times. This is going to take me forever. All right, same setup. Hey, what if I want to do some sales and it's a sample? Add them all up, divide by it. I don't think you guys are going to find this part very hard. The difficulty is, if you notice, I'm doing samples of size like 10. You don't want to do this by hand for anything bigger than that. just keep that in mind. Yeah. All right. So here's that same example with the balancing point. This one looks a little bit more like what I was talking about with the ruler and the dice, where I've got some blocks. So imagine them having weight, so there's some heft to this. The one all the way out at 90 is going to have a little more force than the one at kind of close to 0. So of course it makes sense that 30 would be the balancing point, given the fact that most of the data is about at 20. Yep. Cool. So keep in mind, same stuff. Hey, it's in the center because it's by size. If you look at the deviations again, you get 0. I keep bringing this up. I probably shouldn't have done 2 slides of it. But be careful. That's not how you're going to figure out how far away things are. And there is a way to fix this. It's probably what you're guessing. If everything's negative, I'll just make it positive. So, one thing to really watch out for with the mean is that it's very sensitive to extreme values. So I'm going to take that original data, as you can see in the top box, and just add something that's really far off from everything else. So this wouldn't have fit on my ruler in the previous image. So we've got, like, you know, our typical mean sales, and all of a sudden you make one really big sale, 390. Oh my gosh. Look what happens to your mean. It goes from being 30 to 60. It doubled. The mean tends to move towards extreme values because it cares about size and it wants to balance things. And this can be a bit of an issue. All it takes to have somebody end up with a value for the mean that's extremely far off from what it normally would be is to somebody accidentally mistype a 0 in your data and to add an extra decimal place, or end up accidentally, you know, just throwing a 0 into something that should be non-zero in general. Like, imagine you're looking at a population's age and there are a bunch of adults and somebody accidentally throws a 0 in there. Well, adults are generally considered to be over 18, so clearly that's going to throw everything off. And, you know, missing one little part like that is quite extreme. We're going to do a graph in a little bit that does a good job of detecting those. Alrighty. So here's another example of looking at how extreme values get affected by the mean. Again, I'm showing you some Excel just in case that tends to be your bag, man. So here's the starting salaries of some accounting graduates, and if you look at the average, you know, it's about what you would expect. Looking at the values and ordering them by size, you might guess it's somewhere around 50,000. Doing it exactly, you get the value I have in the green box below. Sorry for those of you who are colorblind, I did not pick Excel's color layout. Man, it's the thing that's in a box next to mean. If somebody turns out to be an accounting grad and an NFL draft pick, we get one more item in our data set that's really, really far away from the rest of them. And look at what it did to the mean. Just one value, as long as it's really far away from everybody else, can really make the mean not very useful. What do I mean by that? So remember, our goal with centers is to have something that represents the typical or average or central value in our data set. So looking at that first set of starting salaries, 51,000 seems reasonable. Yeah, a lot of people are around that salary. Some are above, some are below, but they're not that far away. But when you look at that second data set with our NFL draft pick, is anyone even close to 30? Sorry, not 30. $332,000 a year? No, in fact, they're all pretty far away from it. Even the one who got the NFL draft pick is far away from that. But because it's needing to balance out this extreme value, your mean ends up being in a really wonky spot. This is also one of the reasons why when I know that I'm going to have some extreme values in my data set, I don't like to use the mean. Alrighty, so just to run through this again. Uses all the data, extreme points mess it up, it's a little wonky. Deviations don't really work well for it, so how are we going to do distance away from center, or spread as it's known? Let's find out. Oh no, wait, I gotta do mode first and median. Crap. Let's talk about the median. The median's actually my preferred method of telling where the center is of data because I know it's not sensitive to extreme values. It cares about order. I know the symbol that your textbook likes to use is MD for median. It is not the most popular symbol for it. It's actually just capital M. I will probably use capital N just so you're nope, I'll do what the book does. I might accidentally use capital M a couple times. Fun. Anyway, so how you figure out where the median is you can take the number of datas that you have, arrange them in order, then find the halfway point. Now, if your value in the data set, if the halfway point is a value in the data set, you will just use that value. If it is not, you'll take the average of the two closest. So what I'm saying is if you have 5 values, obviously the center one will be the one in the 3rd position because it's right at the center. But if you have 4, there's no value in the middle that'll split it into 2 and 2. So you average the 2 that are closest. Does that make sense? I hope it does. If not, my examples should help you out. Here we go. So, oh, this was my one about outliers. Damn it. I thought this was in the other order. Sorry. So the median for the first group, hey, notice it's 3. And if I add an extraneous value like 10, it's still 3, which is hilarious to me. Yeah. So it's just like if you imagine a classroom full of students and you think about what the average height is, it's probably like 5'11", 5'10", maybe 5'9" if you've got some people that are like me, not very tall. And then you suddenly let a giant join your class who's 10 feet tall. Hey, the median is probably going to maybe go up like an inch or maybe not at all, like this one. But your mean would go up probably to like 8 feet, which doesn't even make sense. Was there somebody who's been 8 feet tall? I don't think so. Anyway, so let's compute the median. So I've got my accounting grads here again. So notice there are 7 data sets here, or sorry, 7 salaries here. So my size of my sample is 7. So I'm going to order these first. There we go. So I've sorted them from largest to smallest. It doesn't really matter what order you do this in, but I tend to do it from smallest to largest. Then I got to figure out who's in the middle. So since there are 7 pieces of data, I'm going to divide that by 2 and get 3.5, which means it would be the 4th from the top or the bottom. So you calculate either starting from the top, 1, 2, 3, 4, or starting from the bottom, 1, 2, 3, 4, and find that your median would be 52,000. Yay! What do you do if you don't have a nice even number of that? So here's the example I was talking about where you have to average the center. Here it tells you it's 5th from top and bottom, but there's actually 2 values that are 5th from top and bottom here in this data set. So it's 20 and 20 in this case. And when you average those two, you get 20. So when you have an even number of data points, you're going to end up figuring out who the middle 2 are, averaging them, and placing your median there. Now, don't think this is going to be a problem because even though we tend to say centers are the typical value of your data set, they don't have to be a value that's in your data set. So in this case, it actually is. 20 is a value in the data set, but if you were to physically position it, it's actually right here in the center between the 2 of them, not the value 20 in the first part or the second part, which is a little unusual, might not be something you're used to. But the mean is neither of those anyway. It's never a value that occurs in your data set. I shouldn't say never. It rarely is a value that occurs in your data set. Woohoo! And then once again, if I took that same data set where my median was 20, if I added an extreme value, well, it doesn't do anything. Watch what happens. It was right here, and then you would just move over one, which is hilarious to me. I mean, yeah. Going back to the accounting grads, if you add in that extreme value and do the median, notice it does move up in position. So here it was 52,000 because that was in the center. And then, I forget you guys can't see my mouse. I gotta tell you, the new Microsoft really has me pissed off because it used to be it highlighted my mouse and showed you where it was. Now it doesn't do that at all. It's really annoying. Anyway, looking at the first set of salaries, if you look over there, the median is 52,000 because it lies directly in the center when it's ordered. And however, if you look at the second set of salaries, which includes our NFL draft pick or extreme value, what it's going to do is, since there is now not 9, I was going to say there's 9 values, there's 8 because the first entry is 1. I always forget that about Excel versus Minitab. There's 8. It's going to be the middle 2, or the average of 52,000 and 56,000, which comes out to 54,000. So it moved up 2 grand. Did it get affected by extreme value? Yeah, it moved a little, but not enough for it to be significantly different. So here I would use the median to describe the center of this data because of that extreme value. Yay! Why did I include this slide? Judge me for this. All right, so why do I want to use the median? It uses only the middle values by position, not by size, not as sensitive to extreme values. So if you suspect your data set might have some extreme, like low values or extreme highs, you should use the median. The median is what people mostly use for salaries anywhere, because you'll always have C-level executives that make a significant amount more than the average person working for the company. The other thing is you'll also have interns who maybe not making anything, so that's quite different from somebody who's a salaried employee or manager who's been there for 10 years. So talking about what a typical employee makes is a little bit difficult for those of you who are interested in salary data analytics. Alrighty, let's talk about the mode. The mode is the most frequently occurring data set, so data place in the data set. So here you just need to watch out for who shows up the most. It is quite possible that you have a mode. It is quite possible you have many modes. It is quite possible you have no mode because everybody occurs the same amount of times. You don't have to have a mode, just so that's clear. And in this case, it's 20 because it occurred 3 times. The mode's kind of boring. It's a cool name, though. Maybe name your band Mode. Maybe we should get Mode t-shirts. Anyway, oh yes, this example. So this is actually taken from real data of a number of absences people missed in a class. This one makes me mad because, like, who misses 5 days? That's just, like, a lot. In a 15-week semester, that means you missed, like, a third of the class. Maybe you were sick. I don't know. Either way, most people only miss 1 to 2 days of a class in a typical semester, hopefully for good reasons, so it makes sense that 1 comes up as our mode. Not too much of a shocker there. Good times. This example is taken from a data set that you can find online in the extra materials for our course. This is the weight of NBA players. I've used this one before. I accidentally called it heights in my first video, so that's awesome. So what I did here is I arranged a table where I was doing the frequency of the weights and how often they showed up. And there's quite a few values that come up very frequently. However, 235 pounds comes up the most at 33 times. So that would be the mode of the NBA players' weights. If you're wondering how you're going to do this for really large data sets, the answer is technology, because reading through and doing what I did here, that's very time consuming. It's much easier to ask something to calculate it for you. Oh yeah, this is the Excel code that does it a little bit faster in case you want to know. So if you just have the weights listed in one column, use mode multi, it's much easier to use. Fun facts. Oh, and the reason why you want to use the multi version is it also checks for multiple modes, because with weights it could be like 2 or 3 weights that end up being the mode. I'm not even a third way through this. So mode, just as a little review, most frequently occurring, not affected by extreme values, but I mean it's useful because you can use it for lots of different types of data. It's not as popular for interval and ratio data. It's more popular with ordinal and nominal, just so you're aware. But you can do it for all of them. And also you can have lots of modes. I know it says like 2 down here, but you can have multimodal graphs, or sorry, multimodal distributions as well. All right, let's talk about shape. So the typical descriptors when it comes to looking at a distribution is you want to describe shape, center, and spread. Whoop whoop. So this is a very typical shape. It's what we would call symmetric. There are lots of ways to be symmetric besides this. All symmetric means is that when I look at the center line through the data, it looks the same on both sides, or it's got reflection. If you were ever a little kid who got to play with what's called a Miri, it was a little thing where you like put it down on your paper and it made a reflection of what you had so you could draw the other side. They were fun and usually red. Yep, maybe lost half my audience with that one. All right, here's a typical graph of what you'll see for what's called skewed data. So skewed data is data where a lot of your values occur on one side, and then you've got a couple values that kind of occur towards the other side. So this is called left skew because my couple of values occur over here. We generally call this the tail. So if you think of this as like the fin on a dinosaur's back, this is the part that would be on his head. Or sorry, this would be the part that would be on his tail. This is the part that would be on his head. I know that's dumb, but that's how I remember this. And same thing with the right skewed, like, oh, look, the tail's over here on the right. Watch out for the tail. It'll get you. And maybe it's got spikes on it. That was inappropriate. Anyway, so the median, think of it as splitting your data in half exactly by order. So here it would be like if I was going to take paint and color the 2 sides of the graph split by the green line, I would use the same amount of paint because it cares about keeping the same number on one side and the same number on the other. Whereas the median cares about size. Remember, the median gets pulled by extreme values. So although a lot of your data is right here close to the mode and the median, unfortunately the mean is like, oh man, no, look out, I got them tail values I gotta get towards, because those extremes, I gotta go close to them. So the yellow mean line gets moved over a lot more. And the mode should occur at the peak because that's the most frequently occurring. Good times. Let's talk about doing a weighted mean. I'm very sad that I'm only about halfway through this. So weighting simply allows you to cause certain values to be worth more than others. We would normally use this for a class where your grade point averages are, sorry, your points are weighted by certain assignments. So if your tests are worth more than your homework, and say like your tests are worth like 50%, your homework's only worth like 10%, the weights for that would be 50 and 10. I have a good example using just what I've described in our extra videos for the course. So if this looks crazy, go watch that video. It's much better than the example I picked from your textbook here. Anyway, population and sample version look the same. Not a shocker there. I keep bringing this up because there is some stuff for population sample that look different that we've got coming up. So just, keep that in mind. Let's look at an example. So suppose that you're looking at some different types of mutual funds, and you know that, certain parts of it are weighted by shares. So this is the same as saying, like, here's my percentage return. Some of them have that return, some of them don't. So if I want to do the average for my total number of shares, I need to include the fact that different shares have different weight. So here we go. So they're weighted by number of shares here, not percentage of return. So these are actually backwards. That should be the other way. It should be, yeah, it should be W here and X there. I'm sorry, this is written incorrectly. Yeah, because this says W times X, so it should be W times X, not X times W. Sorry, it's not a big deal because X in multiplication commutes. 2 times 3 is the same as 3 times 2. So notice the 2,000, 5,000, and 12,000 in the numerator are what occur also on the bottom. That's what's making my weight. So we're taking the percentage of returns and doing it by size here. And that comes out with my average percent return is 6.35% overall. Interesting? So what you were averaging here was the percentage return, but by size of the shares. They were making my weight. Alrighty. I meant to cut this. We're not doing anything with percentiles, so ignore that part. But quartiles are very important. So the median splits your data in half, and it forms what's called the 50th percentile, because 50% of the data will be below, 50% will be above. We also are going to look at what are called quartiles, because they will split your data into quartiles, so quarters. So the first quartile has 25% of the data below it, and then 75% above it, and the third quartile has the exact opposite. It has 75% below it and 25% above. Let's do some quartiles, because these we're going to actually do. Good times. So here's some data that I've arranged in order, just like we would do if we were starting to do the median. So you can imagine the median here is going to cut this directly in half. What we want to do is we want to find the first quartile. So since the first quartile is in the 25th percentile, so 25% lies below it, we'll multiply that by 19. That tells us that this is going to be in the 7th position roughly. Sorry, 5th position, because 4.75. So I want to use the 5th starting from the lowest. So that would be 1, 2, 3, 4, 5. There's number 51. Similarly, you can find the third quartile from counting from the top doing that, since it must be in the 5th position from the top. 1, 2, 3, 4, 5. So the 5th quartile, provided you can see my mouse doing this, is at 88. That was horrible. Yep. So here's how you would do the quartiles using Excel if you like to do that. Notice that the very last item in that Excel formula in that first top circle is a 1. That's telling it what quartile you want. So if you put a 1 there, it'll give you the first quartile. If you put a 2 there, it'll give you the second quartile or the median. If you put a 3 there, it'll give you the third quartile. Woohoo! So a box and whiskers plot is a graphical representation of the quartiles, 1, 2, 3, and along with the minimum and the maximum. So it starts out in that order. It starts the min, puts a line for the first quartile, and then it makes a box connecting the third quartile and the first quartile, and usually you put a line through the center of the box to represent the median or the second quartile. Alrighty. Oh, this is exactly what I just described in the previous slide. Yep. Usually when we're doing this, we'll identify what's called the interquartile range, or the spread between the middle 50% of the data. That's the distance between Q3 and Q1. So take a note of this slide, because knowing how to do this physically is kind of important. We're going to use technology to do this most of the time, so it's not so important to do this. You'll notice that pretty universally, everyone marks extreme values that are outside your quartile range with stars for this. Or dots is another one if you use a TI-80 calculator. Or anything from the 80 series, or the 90 series does that. Were they invented in the 80s? I don't know. Anyway, so your book makes a real big deal about upper and lower limits for the quartiles. These are only going to matter if you have outliers. Otherwise, for your upper and lower limit, you should be using the median. Or sorry, that was a misspoke. Otherwise, you should be using the minimum value, not this lower limit value, which is incredibly incorrect on their part. Anyway, so here's your first quartile. Notice here's this middle 50% box. Oh, I always forget you can't see my mouse. I hate this. Little stars for extreme values or outliers. These are ones that are more than 150% away from your data's distance from each other. So notice the interquartile range is from Q3 to Q1. That's the distance of 50% of your data. So this 1.5 times it for the lower limit. That's saying, oh, this is the middle 50%. Let's go 150% away from that. And if you're further than that, I'd say you're very unusual, because compared to everybody else, you're really far away. And that's how you get the upper and lower limits. You start from the quartiles and you go 1.5 times the distance away in either direction. So that's why the minus from the first quartile to go below, to go down 150%, and then plus from the third quartile to go above, and that's how big it could be. So these stars down here are what we would call lower outliers, because they're below the lower limit. You can also get them above. You can also not have them at all. Yay! So here's a picture of what one looks like on Excel with its upper and lower limits, and along with its outliers. And don't worry about this so much. I'm going to do a lot more examples with this with Minitab that I think you will like a little bit better. We're also going to compare some box plots so we can get some idea of how to know where things are. My big critique with Excel is it's very hard to see the median in their box plots. I do like that you can color code them, but you can color code everything on Minitab as well. All right. Beware of levels of data before computing your numerical measures. Why am I bringing this up? Well, because you can't really do the mean of something that's qualitative because it doesn't have units. What do I mean by that? Oh my gosh. Well, you can really only do the mean of interval or ratio level data. So age, income, sales, temperature, these types of items, things that have units and either have a true zero or not, but have some sort of scale or order to them. You can't do the mean to ordinal data. Here's an example of something that you 100% actually shouldn't do. So like, I don't know, in your notes, mark this with like red exclamation points of no, 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 don't do this. And this is incredibly common for people to do. So what they'll do is they'll take something that's ordinal, like education level, and they'll give it number values instead. So instead of using the actual words like high school and college degree or graduate degree, they call it 1, 2, 3, 4, 5. Because it has order. It's in order 1, 2, 3, 4, 5. But how far is grade school from graduate school? For some people, that might be 30 years because they go back to school later. So is that a real distance? Is that some sort of unit of measure? I don't know. There is no unit of measure because it's ordinal data. It doesn't have units. So does its average mean anything? Well, no. So if you do the average of this, X bar, here it is again, you get 2.8. What is that? Is that high school or some college? How much college? 0.8 of college? I don't know. That's nonsense. I'm getting a little crazy. Don't do this. If it's words, the average of a word is nonsense. You shouldn't try to make it numbers when it's not numbers. Just saying. Also watch out for this with scaling questions. This is really popular. This is the same thing you'll see happen. You'll take agree, strongly agree, neutral, disagree, and strongly disagree. That's what those letters stand for like SAA, neutral, D, SD. I should have actually written out the words rather than writing this. What was I thinking when I wrote this? I don't know. Anyway, do the average of that by making them numbers like 5, 4, 3, 2, and 1. This is just like when you read the average rating on Amazon. Does it really mean something? Is it 4 stars or 5 stars? I don't know. Do they agree or are they neutral? Let's find out. Add them all up and divide by 9 because there's 9 of them. You get a 3. Everybody's neutral. What? Does that seem reasonable? Or does it? But look at your values. Do I have more 5s and 4s than I do 2s and 1s? I mean, what's happening? Or do I have mostly 3s? This is worthwhile thinking about. Is it really neutral? Yeah. So the mean is like something you only can do to quantitative data. Be very careful. Don't assume because somebody codes something or calls it 1, 2, 3, 4, 5 that it's numbers. Remember, without units, it's not quantitative. All right. I think I've beat this a little bit too much. Are you married or not? What does the mean of 1.9 mean? It means I'm single, but maybe I'm married. Are you engaged? This is stupid. I'm sorry. One more time. If it's ordinal, don't make it numbers. Okay, so for the median, our rules are a little bit different. So since it cares about order, all I really need is stuff that has an order. What does that mean? It's okay to do to ratio or interval because they naturally have an order as something that's quantitative, but you can also do it to ordinal data. Don't do it to nominal though, because nominal doesn't have an order. So the median is useful for stuff that we've seen before that did not work with the mean. So here's some warnings about these. This is a nice little summary table. Maybe if you're somebody who's not printed out the notes, you could take a picture of this on your phone because this is some good things to remember. I tend to prefer the median when I don't know what my data really looks like. Watch out for using the mean because it's one of those popular guys that everybody uses and talks about and knows how to do. Yeah, but really is sensitive and doesn't always work. And you can only do it to certain levels of data. So if you look at the summary we're looking at here, pay attention to that data level common quite a bit. Sorry, data level column? Ooh, couldn't get that out. Because when you look at this, the mode is the one you can really do to the most types of data here. Whereas mean, you can do it to the fewest. You can only do it to ratio and interval. So you really got to be sure what kind of data you're looking at before you attempt to pick a measure of center. Not just picking one and seeing what you get and which one's useful. That's how the naive person approaches these kind of problems. Alrighty. So be careful also looking at the mean and median. If you have small data sets like the one I have here, it's very easy to have no differences in what your mean and median are. That doesn't mean that they're good descriptions of your data necessarily. For this one, actually, I would prefer to use the mode in both cases because the mode would actually be the same for what you're seeing in Department A. It'd be like, oh, the mode's 100 because the 100 happens the most often. And then in Department B, you would get 90 and 110. So those seem different than what was happening here. The other thing is, like, just because my mean and median look the same and end up being the same doesn't mean my data looks the same. Look at A and B. They're totally different. Well, I mean, they have some data values in common, but if you look at how they're distributed, aka what values they might possibly be, they are very different. So clearly just knowing the center isn't enough. Maybe it's time we talk about some spreads. All right. Oh, here's some graphical representation in case you weren't sure. So clearly Department B is very differently shaped from Department A, in case that was unclear. Sometimes putting it on a scale really helps you see that. All right, so let's talk about measures of spread, aka measures of dispersion or variation. Variation is about how different you might be from each other, and dispersion is about how different you might be from the mean. So be careful. We're going to look at the following: range, variance, standard deviation, and coefficient of variation is the one we're not doing, even though I have it on this table because I stole this from your textbook. Is it really stealing if I tell you that? No, I'm citing my sources. I gotta watch my verbosity. So here we go. So range, interquartile range is one we'll also do. It's one I've already talked about, so I'm going to do very little with that, so look out. but it is a measure of variation. Variance, which is literally the OG of this, it's how much variation do I have, or how much variance from the mean do I have. And then standard deviation is actually the most popular one. It's the one you're going to see used the most often. It's the one we're going to use the most often because it tells me how far away I am from the mean on average using deviations, which be careful. Earlier we saw deviations are problematic because if you add up all your deviations, they come out to 0. So how am I going to fix that? We're going to math it up in here. All right, so the range is actually very simple. The simple version of the range is just the maximum minus the minimum. It's how far apart your data is. The interquartile range is just your difference between Q3 and Q1, or your middle 50%, or the distance of your middle 50% if you like. The variance is going to attempt to kind of figure out how far you are from the mean, or how does your data vary from the mean. The problem with the variance is that it's what we call bloated. It gets very large very quickly and doesn't do a good job of representing how things vary because of that, because it can make a small variation seem very, very large. Too many V's in there. And then standard deviation fixed that problem by just bringing your scale down using one little thing. And again, we're not doing coefficient of variation. Okay. Let's talk about some range. A measure of variation that is computed by finding the difference between the maximum and minimum. I have already said that. It's very simple, very easy. It's a quick and easy one if you're looking to compare a bunch of different data sets to each other that are about the same type of data. Usually what I'll use is the range because it's the one you can easily see off a graph with just looking at it. The only downside to the range is it only pays attention to the min and the max, so it doesn't care about much what's happening in the middle of the data. It only cares about what's happening on the ends, which is some rather extreme way of looking at your stuff. That's what I mean when I say it ignores the data distribution down at that bottom. It only pays attention to the ends. You know, it's like watching a movie and just seeing like the beginning scene and the end scene. You missed a lot in there. All right. So taking a look at this raw piece of data I've got here. So these are years of staff experience from, I think it was an accounting firm again that this was taken from. Go memory, go. So there's 100 people here. Oh gosh, there's quite a lot of variation here too. So if you notice, there are some values that are below 10 years. There's some that are above. There's a lot of things that are double digits. But it looks like nobody is bigger than 20 years. Let's take a look at how we might describe this data using dispersion. So this is a frequency table of the years of experience, and you'll notice the lowest we have is 6 and the highest is 17. So if we were to just use the range, your answer is I have a spread of about 11 years amongst my staff in their experience, or years at the company. Woohoo! So again, easy to compute, high minus low. It's sensitive to extremes though because it uses the min and the max, obviously. That one you probably would have guessed without me telling you. All right, let's take a look at the interquartile range. The interquartile range is a lot more stable than the range, which is one of the reasons why it's used over the range. It's also fairly easy to calculate. It eliminates the problem of what we have with the min and the max being used from the range. It's not going to be as sensitive to extreme values. And it just gives you the middle 50% since it's based on the quartiles. So as a reminder, here's an example using the interquartile range. Now be very careful in reading this box plot. One of the mistakes I see people make is they forget that the distance between the quartiles, if one of the parts of the box is bigger than the other, that does not mean that there's more data there. It has the same amount of data in it. So what I'm saying is if you look at the box going from Q1 to Q2, it's shorter than the box from Q2 to Q3. What that means isn't that I have more data from Q1 to Q2 than I do from Q2 to Q3. It means that my data is more spread out there because it's the same number of people from Q1 to Q2 than from Q2 to Q3 because it's split into 25% pieces. Yep. So if I had 20 people, each of these 25% would represent 5 people. And that means that when I look from Q1 to Q2, my 5 people there are farther apart than my people that are in from Q2 to Q3, but there's still only 5 of them. Not that there's more there, just more spread. Anyway, hopefully that was something you listened to and you got this far in the video to make it to this. But the interquartile range is just going to be Q3 minus Q1. So for this data set, that's 57 minus 30, or 27, which I think is more representative of what's happening here, or more typical than using maybe the range, which from here would be 70 minus 12 or 58. So I tried to draw on this and things went bad. I don't know what happened. Here we go again. So remember back when we had deviations and we were looking at everybody's distance from the mean, and when we added them all up, we got 0 every time. Here's how you fix that. Well, if they add up to get 0, let's just make everybody positive, because then nobody will cancel if some are negative and some are positive, like we had with the deviations. So what they did is they just squared everything, because that forces everything to be positive. So you'll notice in the middle of this equation, you'll see xi minus mu, distance from the mean, my deviations, squared, and then you add them all up and divide by how many there are. So that add them all up and divide by how many there are, that's sum divided by n. That's the averaging. So what this is trying to do is it's trying to do average distance from the mean, but there's a square in the way. And one of the things you know about squaring is it doesn't just make things positive, it also makes them bigger, because you know that 2 squared is 4, which is twice as much as what it was originally. But then when you do 3 squared, you get 9, which is, you know, 3 times as big, not just twice as big. So not only is it like getting bigger, it's getting bigger by the factor of itself, which is huge. That's what I mean when I say it's bloated. It gets big quick. All right. So here's looking back at our data that had the same mean and for both departments. And why am I still doing this? Ah, yes, I want to do dispersion with these. Let's see how they're spread, because we noticed in their graphs they looked very different. Let's do some spread with this. They have the same mean. I already said this. Let's look at doing their variance. So what I'm going to do for each of these values, look at the table down below. That's just the inside part of this equation, the stuff between the parentheses, difference from the mean, and then squaring it. So I took 99 minus 100, 100 minus 100, 101 minus 100, and got those values, and then squared them. Then you add up all those values, that's where that 2 comes from in the fraction up top, and then divide by the number that you had. I had 5 items in Department A. That gives you 0.40. Got it? So it's do the distance, square them, add them all, then divide by how many I have. So you got to work your way from the inside out. So if you remember back to your please excuse my dear Aunt Sally, start with those parentheses first. And it's different from that because you're doing it for every single value of x, or every single value of your data. We're going to do the same thing for Department B. So you take all of your x's, the 90, 100, 101. This has a typo in it. This should be 110, 110, and 90, 90. Crap. All right, well, I got it right on the second column. Forgive me, I have made typo. I am too tired to fix this right now. That makes this confusing. Can I pause this and fix it? Hold on. Yep, I can't pause it and fix it. I'm so sorry, guys. So the x value should be 90, 90, 100, 110, 110, and it's not. I've used Department A again. It should be Department B's values. I apologize. So you go through and you take all those, subtract the mean, so you get a bunch of values, then you square those values. Notice I'm getting a bunch of hundreds and some zeros. You add those all up to get 400, and then you take 400 and divide by 5 to get 80. How much bigger is that? Oh, it's so much bigger. Just as a reminder, Department A's spread is 0.4. Department B's spread is 80. And now here's why 80 and 0.4 don't make a whole lot of sense. So remember, these both had the same center, 100. Well, if you look at 100 and look nearby 100, like the distance 0.4 away, because that's how much spread this supposedly has, so you go 0.4 in each direction, you get most of the data. But if you try that with B, you get like everything. It's ridiculous. The spread is just way too large. So starting at 100, if I go 80 above it, that'd be at 180. That's way past everything. And then if I start at 100 and go down 80, I end up at 20, which is way past everything again. So what's weird is if you look at A, you just get the stuff at 100 using that spread, looking at the spread around it. And if you use the one for B, though, you get everything. So it's too much variation. It doesn't feel like it physically means anything. And if you're struggling with what this means, I'm going to do standard deviation in a minute, which is basically variance's big, better brother, whatever. And it fixes this problem of this doesn't physically mean anything. Yeah. Crap. So let's look at the better one. So remember, the square was the problem because it made everything too big. if you were to guess back in the day how this would be fixed, you'd probably guess exactly what they did. Let's just take the square root of it. Also, the jerks who named variance, if you notice, they named it sigma squared, the little circle line dude with the square, because they knew that when they square rooted it, then they could just call this one the circle line guy, which is just sigma. That's pretty lame, right? That's what I thought when I saw this too. Math people think they're so clever. Square root of the square is the original. Blah, blah, blah. Sorry, now I'm getting sassy. Anyway, so the problem was squaring to make everything positive made it too big, so we'll square root after to make it smaller again. And this fixes everything. So now what we're going to do to get the standard deviation for Department A and Department B is I take the variance, also known as sigma squared, and I get sigma by just taking the square root of it. So my standard deviation for Department A is just the square root of 0.4, which is about 6. If you look back at the graph, or sorry, 0.6, that makes sense. And Department B, it's about 9 when you do the square root of 80. And if you look at your data, it was centered at 100, and half of my data was at 90, which is 10 away, and half of it was at 110, which is 10 away in the other direction. So does 9 make sense? Yeah, being almost 9 makes a lot of sense. Although most of them were at 100 too, so that kind of messed things up. That's why it's not exactly 10. All right. Now, one thing to watch out for is that when you're doing the sample standard deviation, instead of using n and the denominator, we use n minus 1. Why on earth does this happen? Because when you look back at the mean, every single value of x is already in there and being calculated, which means everybody is in there at least one more time than what they should be. That's why we divide by n minus 1. The other thing is when we're dealing with sample standard deviation, we use s to symbolize it. This is supposed to be a lowercase s, not a capital S. So then we use s squared for sample variance and s for standard deviation. We will be using little s more frequently than anything else in this entire class. So just keep that in mind. Just use s. It's a thing. All right, let's do another example. So here's a smaller data set. Again, smaller ones, easy. We can do it by hand. Not smaller ones, probably not going to do that. So these are restaurant sales. This was a random sample from an entire night. So it's, got a little bit of variation to it. I think this is a couple years old. I think this is from 2001 because these is way cheaper than what I would spend going out for a night. Anyway, so the first thing you're going to do if you want to calculate standard deviation is, since you're going to have to be doing deviations from the mean to do this, you need the mean first. So the first step is always calculate the mean. Add them all up, divide by how many there are. In this case, you'll get $23.61. Notice I'm rounding to 2 decimal places because this is money. It makes sense to do so. In other cases, you don't want to round too much and you do it too many places or else you might have some problems. Now when calculating s, I'm going to look at everybody's distance from the mean, square it, and then divide by, and since this is a sample, 7 minus 1 before I take the square root. So keep in mind, I'm dividing by 6 and then taking the square root. If you're watching this at home, I would take a moment and pause this video, go through and do this calculation yourself and make sure you get the same result I did. And keep in mind, round it to 2 places because it's money. So here, my standard deviation will be $4.31. All right. Last but not leastly, let's talk about z-scores. Z-scores are what we're going to use when we want to tell, is a single value of x unusual compared to the rest? Or how far away is my value from typical? What does this mean? So take a look at that first equation there. Z equals x minus mu over sigma. So remember, mu stands for mean, sigma stands for standard deviation. Mu is a center, sigma is a spread. So mu is like the middle dude, and sigma is how typically spread average distance from the mean is what it is. So it's how far everybody is from the mean on average. So really this is saying, like, how far is x from mu by doing x minus mu? And how far away is it compared to everybody else on average? Or how many standard deviations am I from the mean by doing the difference between the two and then dividing by standard deviation. Typical z-scores are fairly small. If it's close to 0, that means my numerator was close to 0 or my x value was close to the mean. If I have something that's farther from 0, that will mean that I'm more unusual. So most z-scores are around 1 or 2. Even 2 is fairly unusual. You get 3 or farther away from the mean in either direction, and you end up with something very unusual. Another thing to keep in mind as you look at this is that having a positive z-score means that when you did x minus mu, you got a positive because standard deviation can't be negative because it's got a bunch of roots and squares in it. So when looking at x minus mu, that had to have been positive. If this was positive, that means the thing I subtracted had to have been smaller, which means my x value had to be above my mean. So that means it was a higher value in my distribution. And if it's negative, that means x minus mu had to be negative, which means it had to lie below the mean. So really, the positive or negativeness of a z-score tells you its location. Is it above or is it below the mean? And then its value tells you whether or not it's unusual. You might ask, what am I going to use this for? It's to see where something is located at in your distribution, and it's also so you can compare values from similar data, but slightly different data. All right. Oh, how do I standardize? Well, you need to do the mean and the standard deviation, and then you do your subtraction and your division. That's not too hard. I literally just took those 2 complicated looking steps and made them very simple. I hope that was okay. All right, so suppose I'm looking at IQ scores. So IQ scores, we already know what they look like. They tend to be very bell-shaped and very normal looking, with a mean of 100 and standard deviation of 15. This is the old IQ test. The new one, I think the mean is 120. I'm wrong about that. It's something else. Anyway, let's pretend somebody has an IQ score of 121. Let's see how unusual that is. So what we would do is we'd subtract the mean of 100 and divide by 15. This tells me that their z-score would be 1.4, which means it's positive, so they're above the mean, and it's about 1 away, so it's not unusual at all. And if you want to look at this physically and what it exactly means, it means that the score of 121 is 1.4 standard deviations higher than the mean IQ. It's 1.4 above average. So let's pose ourselves a little question. Suppose you applied to 2 different universities, University A and University B, and they have 2 different entrance exams. One's on a 100-point scale, one's on a 1,000-point scale, and they have different means and standard deviations, different centers, different spreads, because they're totally different tests. What we want to see is which school did you do better on their entrance exam for, or did you do about the same? There's only one way to find out, and that's to compare our scores. Now they're on totally different scales, so we're going to use z-scores to solve this problem. This is also how you can compare different athletes from different, well, not from different sports, from the same sport in different years, because the rules change every decade or so, and that can make scoring or not scoring very different. My biggest thing is when they changed all the rules for hockey. I didn't like it. You guys might not remember that because you're probably younger than me. Here we go. So what we're going to do is we're going to calculate the z-score for A and B. So we're going to pretend that your scores are where I have the arrows. On A, you got an 88, and on B, you got a 798. Keep in mind, I don't know who's better. Let's do some calculating. So what we're going to do now is we're going to do what's called standardizing or studentizing. That's the older name for this. We're going to take the values of x we have, or the variable for the test scores. We're going to subtract the average test score, the mean, and divide by the standard deviation. So I've highlighted this in orange. So on the first test in University A, we subtracted the mean, got 18. So I did 88 minus 70, got 18. Divided by 10, got 1.8. Boom, your z-score is 1.8. So you're 1.5 standard deviations away from the mean. You're a little bit higher up, not that far. For University B, we subtract the mean of 750 and get 48 and divide by the standard deviation of 70, which is, going to give you a 0.69. That's not very far away from the mean at all. In fact, that's a good sign that you're not very unusual at all. Let's see what you look like on a bell curve. Now, if you're wondering how I'm placing this, I'm using something we have later called the normal curve. But for now, just trust me that it looks like this when you do the z-scores. The center is 0, and the standard deviations fall about where I've placed them. Forgive the terrible coloring. It's what I do. So I've placed your position based on your z-score in University A and in University B. Who did you do better on? Well, the more far you are away from the mean, the more unusual you are. So the higher your z-score, the better you did compared to the others. So in University A, you clearly did better than you did for University B because you're farther away from 0 in A than you are in B. Might want to go to A. Hey, I stole some of this from your book. I didn't steal it though because I cited it. Using it for our school is fine. Producing a copy for yourself is fine. Selling it to other people is not fine. I have to warn you of this simply because I used stuff from your textbook in this lesson. Sorry about that. If you're worried that you're going to do terrible in chapter 3, we are doing lots of mini-tab and I have lots of extra examples. So make sure you watch some of the other videos, especially for this chapter because it is calculation heavy, and especially if it's been a while since you had algebra and you're feeling a little rough with your calculation skills. See you next time, I guess.